So the plan is to discuss about major connections. It's especially important for the project, from the project's point of view. So hopefully we manage it all this today. Hopefully we will, because we still have a few things to discuss here with the STM8. Because not only we have to finish the addressing modes and the basic, analyze some instructions, some sample instructions in case of capabilities and in case of the classes of instructions, because that's something I would like to do today. But also the basic facts about assembling and linking. Assembling and linking is more universal because, as you know, the STM8 for us is just an example of a microcontroller, giving us some pictures how everything is working, but there are general rules about the addressing modes, about the assembly instruction, and as well I would like to use the STM8 to discuss the possibilities we have in case of assembling and linking of our project. So all this hopefully today and more. We'll see how it goes. So in case of the addressing modes, we've got plenty of addressing modes. So we were circling around addressing modes already recently. But I think the best would be to give you that we discuss them on examples. You know, theory is nice, but theory is nice, but theory is not. It's usually quite far from practical application. So that's why let's put aside the theory. Let's focus only mainly on the practical examples. So the addressing modes on this microcontroller, as mentioned, this microcontroller is a bit rich in case of number of addressing modes because it's closer to CISC. In RISC microcontrollers, usually we have much closer list. Much shorter, but much shorter list of addressing modes. Yes, yeah. If you are aware of the capabilities, then in case of simpler microcontrollers, you will have. It will be simpler, of course. So going back, because we already discussed theoretically, at least, or without examples, some of those addressing modes. Now, with the examples, all the capabilities or all the options we have in case of STM8. So the simplest always present in every microcontroller was the inherent mode. The inherent means that we have the instructions which require no addressing modes. This is what inherent means, built-in. So in other words, inherent is something like built-in. So these are synonyms, at least here in this area. So there is no addressing required at all. So for example, clearing some bit or doing nothing like the no operation. Then we have the immediate mode. Again, we mentioned about this mode. Again, simple mode. Again, always present. So every microcontroller must have this mode because it's about placing some value, some literal, some constant, in other words, because it's actually the same, to put it into a register or into a memory space. In this microcontroller, we are allowed only to place anything into register, so we can load or put something to X, to Y, or to A. So we are forbidden to move the value directly to the registers, although they are to some place in memory. Although, to be honest, there are microcontrollers on the market that are even more sophisticated in this way. So they allow for more. So they allow for placing some data directly into memory. It's rare because it's difficult. So the instruction decoder and the complexity is very high of all the CPU itself, but it's possible. So there are such microcontrollers. In majority of cases, still, we are allowed to place an immediate value in the register. The immediate value, it's characteristic. There is a hash sign, and then we can have a dollar, but we don't need to. So we can place here a decimal value as well. We can put binary value. We can put octal sometimes. Then we have the direct addressing, which means that we are able to put into our register, in case of this microcontroller, a value that exists under a memory address. That's the difference. So again, because I mentioned it last time, That's about placing F5 in the accumulator or X or Y, whatever we choose, in case of immediate addressing. But if you want to place whatever is under the memory cell F5, so in this first page of memory, or in F5C2, so this is the long addressing, because we have three types of addressing. Extended is missing here because it's on the next page. But here we have direct in the first, second, so short and long address. Depending on the address, take a look, no difference in case of assembly mnemonics here. So we just use the instruction as it is, so LD for loading from F5 or from what is hidden under F5C2. Don't be misled about the length here, it's always a byte. This is an 8-bit microprocessor, which means that it transfers bytes. So of course the address may be 2 byte, the address may be as well 3 byte, like here, because it's extended addressing, so there will be LDF, there will be the difference, LDF and the address, because in this STM8 assembly instructions F means extended, so LDF, A, and the address with 3 bytes if you want to reach to the whole memory, but still it will be 1 byte transfer. Then we have the index addressing, mentioned already. Index addressing with no offset, with short offset, with long offset. Very nice addressing modes from the perspective of writing any code in C++ or in any higher level language, because we have it's very easy. Of course, for us, maybe not so as if we would like to write anything in assembly code. But if you will start to do something in C, then these modes are especially suitable for direct translation between C and assembly, because it's very easy for the compiler to compile the C code into the assembly, because these instructions are widely used in C, where we have here we have index. So for example, X may be the address of an array. So in C, very often, of course, in any programming language, we're using structures of data. And in case of structures of data, yeah, we have the whole structure with 100 elements, and we want to get to element 50 to element 15, or to whatever element we want. So that's what we do. Here, it's very simple. So we put in X the beginning address, so the address of the element 0. And here, under the address, or here under this address, we can put the offset against the initial value, the initial address. So it resembles really very much the structures we have in high-level programming, and this is transferred into C, into assembly. In case of simpler microcontrollers and microprocessors, these modes are very often missing. So quite often we've got just index mode, but no offset usually. That's also a problem sometimes, because we need to do more. So of course then if we want to access various cells in our structure, then we need to update this X register or this indexing register, because they have different names. In case of CISC microcontrollers, quite often they are X and Y. In case of RISC microcontrollers, classic RISCs, all the registers are R something. So register 0, register 1, 2, 3, 4, 5. We can use the registers interchangeably, but unfortunately those modes are often missing, which means that we have to play with this mode and we have to update this register that we choose for indexing with separate instructions. And here we have just one instruction that does everything, because this instruction, we are using this instruction, and it will fetch for the offset, modify the X register with this offset value, and then, only then, grab the value from this X plus offset to the accumulator. So we have three things happening with just one instruction. So simple instructions, simple assembly language, but have 3 elements and 3 operations actually happening. Three operations happening, and then we've got indirect pointers. So we have here the pointers, so we have even more advanced addressing mode. So here is a pointer, so it's something like with X, but this time the pointer is hidden under the address, showing us where to take the data from. So it's instead of using X register, we can have a place in the memory where is a pointer to the data. So So it's even it's even a step further. It's even a step further. Yeah, these modes. Okay, sometimes we can have some use of it. They are definitely not available in simple microprocessors and microcontrollers. Then we've got direct relative with short offset. So this is for branching, as mentioned a bit before. This time we don't have, so this is for jumping, so we have no hash, but this is the offset. So this is just a value, so we don't take, it's again a bit misleading, because here for this kind of instructions, for arithmetic and logic instructions, here this $F5 means that we take from $F5 and we take the value that is hidden in this F5 cell. With this direct relative instruction that we're jumping, yeah?
Pointer indexes pointer or data?
This one?
Below. I mean,
This?
short pointer indirect indexer. It's indexing pointer or data?
Indexing pointer. Here, yeah, that's indexing pointer. Here we have the F5. This is the index, so it is minus something. So it's jump to the location which is minus. It's a value. So again, a bit small discrepancy here, because this is the address. This is what is hidden under the address in the cell F5. And for the jump instruction in this direct, because this is the jump instruction, so this is one argument only. This is not the address, but this is the value, the number. So it means that it's the F5. It's -7. So it's jump 7 cells earlier. So it's the execution from 7 cells earlier. This can be used in one by short offset, long offset, or we can have extended offset. So we can have extended address, and then we have the instructions like callf. There can be jump as well, where we can go to extended memory. So for a very long address. And then we have the stack pointer indexed version as well. I mentioned it already previously with the stack pointer, where instead of X here, because these are the same addressing modes, but instead of X and Y register, we are again stack pointer. So again, a mode. Stack pointers are a base, and then we are moving, we are accessing the instructions, the data against stack pointer. So we can have the stack pointer again. It's something that we use extensively, and it's especially extensively used in C, where there are functions in higher level languages. When we are having function calls, so if there is a function call, then very often there is a data put on stack, and that's how we access the data. Yes?
I wanted to add about the jump instruction. We couldn't just go back.
Yes, yes, because this is the value, this is the number. You are going to this value, so you can go to any value you want.
So we would use a call instead of a jump.
The call and jump is different. That the difference is that in case of call, the current address is, so the next instruction address is pushed on stack automatically. So when you make a call, then the current program counter is put on stack, because the program counter is pointing already the next instruction. And the program counter is superseded with this value.
So it's used for functions?
Of course, it's used for functions.
But then it just for example, in if else, when I want to do an if else, I want to jump in the future.
Yes, for if else you're using this kind of jump relative.
But I just can go back.
Yes, because they are going back. They can go back a bit. They go with an offset, you know, because those instructions, the call and jump. For if else, you are going with jumps in general, jumps relatives or jumps absolute, because you don't need to go back from there.
Why doesn't it use an address?
Yeah, an address directly.
Why does it use an offset? Why not
because it's longer.
Yeah,
Because it's longer. You know, when you use an address in this kind of addressing, you have usually, I would put it this way. Usually, we are working in a long, with long addressing, because usually you are working in 64 kilobytes range. Usually, extended is more rare, but it's also possible. The first page, so the bytes from 0 to FF, they are mostly registers, and we don't have much space there, because it's just 200 bytes that are left for our use, even less, because they are mostly registers and they are booked for the microprocessor. So there's scarce of memory. So usually the program is placed into 2 byte space or 3 byte space. If we use call or jump absolute, then take a look. We have to use 2 byte or 3 byte addressing. Of course, this means that the instruction in machine code will be longer. And it takes as well longer time for the instruction decoder to process this instruction. Because simply the instruction decoder must fetch all the data from the program memory, all the address. So it needs more cycle to get the data from the program memory. In case of the relatives of the branches, so of the jump relatives, we go a few cells to and few cells back. So it's like here, we just go, we have 1 byte, which means that we can jump 127 bytes to the front.
Does it calculate it through the addresses?
It adds to the current program counter. That's the difference. Because in jump relative, it takes the program counter. It doesn't replace the program counter.
Just calculate.
It modifies. So the ALU is used this time. 1 input to ALU is used. That's how it's happening physically. That 1 input to the ALU is current program counter, and the second input is this offset.
So if you want to jump
and
back,
the results is
you put a minus.
Yeah, that's F5. That's minus 7.
It can be positive and negative.
And that's minus 10. Not minus 7, because F5 is minus 10. It calculates. Here, with this kind of addressing, we put the instruction decoder takes the value and replaces the current program counter. If there is a jump, or stores the program counter on the stack pointer, on the stack, and then replaces. So that we have the information to trace where to go back. Because of course the call are for functions, so that we are able to return back from the function. That's the difference. The relative jumps, they have limitations. That's something I don't like very much when writing an assembly code, especially if there is just plus minus 127, because 1 byte offset is a very short offset. It's a very short branching we can do. But in 8-bit microcontrollers, it's still fine. In 8-bit microcontrollers, it's still almost fine. Once I had a project that was really a nightmare. It was 8-bit microcontroller with this kind of limitation. But that's another story. Anyway, it's much faster, usually 2 or 3 times even faster than this kind of code. Because the instruction branching is short and it's happening much sooner than the call or go with the full address. Absolute address, because this is about absolute and this is about relative. That's important here is this letter, relative, because it means that we are here and we want to go back or go forward. With this instruction, we are always reloading the whole program counter. Okay, and then we have the extended versions of the instructions that were before. What is interesting? So again, those instructions, sometimes they are useful as well. But I would like to point out again, because I already did it last time, this very nice instructions about playing with single bit. It means that with this instruction, this microprocessor has instructions for playing with single bits in the registers, so that we can test bits, we can clear it, we can set it, we can negate the bits. But single bits, so we can choose which bit to choose, which bit to modify, or which bit we are interested in. That's very important because in case of peripherals, when we play with the numbers, so that we don't care. We are playing with bytes, sometimes with words, sometimes with even longer numbers. But when we have peripherals in microcontroller, like timers, like ADC converters, like various kinds of communication blocks, the timers those peripheral blocks need to be configured somehow. And they have 8-bit configuration registers. But in those 8 bits, for example, 1 bit is for starting and stopping the whole peripheral. So we need to alter this 1 bit. We have bits, for example, telling us that there is a bug or the transmission was successful. It's always 1 bit. So, yeah.
Is there a way to change multiple bits at once, like?
Yes,
clean
there is a way to change multiple bits at once, but to do this, yes, it is possible, of course. We need to use the instruction or the instruction XOR, or if we want to clear the bits, the instruction AND, because this is for setting, this is for negating, and this is for clearing. So then we can do a multiple bit change. Also, we can make the testing as well with ANDing. Also, we can have the testing. That's also used for testing. More about it a bit later on. But in general, that's for multiple bits. So if there is that's also a way. If a microprocessor has no bit operations, then we have to do this. Then we have to use XORing, ANDing, and ORing on the registers to access those single bits. Then we are using masking, and we are testing the registers, or changing the registers with these three logic instructions, which are always present because every microprocessor, every ALU has, of course, support those instructions. Still, this is very nice. I find it really nice, especially in microprocessors, to have this kind of bit operations.
What are the inputs of the operation? It's like the first one is the.
That's the address of the memory.
Yeah, and that's the.
And that's the number of bits. So bit set, bit 1, under the address 1000.
Yeah, so like the second one is like an offset of the first address. No?
This one?
Yeah, like.
This is number of bit. So we have a memory cell. We have a memory. There is a cell at the address of 1000. And this has been 0, 1, 2, 3, 4.
Okay.
0, 1. So this is this bit.
Okay.
That's this bit. That's also fantastic here, comparing to ANDing, XORing, and ANDing, or X or AND, because those instructions in this microprocessor, those instructions can be done on a register, on accumulator, while this bit set can be done on a memory, which means that we can directly modify a memory. We don't need to, because how to do it with ANDing, ORing, and with these logic instructions? First, we have to load to accumulator, then we need to do something, and then we need to store it back to the cell. Here, we can do it directly, so we can use this instruction to modify one bit in the whole vast memory.
We can only change it to 1.
We can change it to 1.
Not to 0.
To 0, yes, because we have bit clear. This is best. This is just the example.
Okay.
This is just the example. So this is bit set to show you the addressing modes, but not. Of course, there are more instructions, and about those instructions, yeah, let's go to see the instructions. Yeah, the addressing modes. They are in the theory. Okay, let's skip it. It's boring, so let's skip it. Okay. Now, categories of instructions, and next important feature, because the addressing modes and the instructions, we'll try to pair them up, because not all instructions allow all addressing modes. So it's more difficult. Some instructions allow some addressing modes. Maybe this way. Addressing modes you have to know, and the categories you also have to know what categories we have in microprocessor. So let's try to find out what options do we have. In every microprocessor, always there are instructions for loading and transferring data. Always, because it's one of the fundamentals of microprocessor, of CPU. That we take the data, we process it, and we move it back. So it's moving the data, and because it's finished state machine with data path, So we have this data path, and data path is about moving and changing the data. A couple of instructions we have here, like loading extended, clearing, moving, exchanging, loading word, clearing and exchanging word, because this microprocessor, although 8-bit, supports in some cases also working with words. That's why W here. Then naturally we've got the group with stack operation. That's another important group of instructions. Always present, although those instructions are usually very simple, usually just 2 instructions, with various addressing sometimes, because it depends. So again, we can have various addressing. Usually most of the addressing is available with this loading and moving. Push-pop is usually quite limited, but still always there always exists the pushing and popping. Here in this microprocessor also pushing with word and popping word, so we can push the whole 2 bytes at once and pop 2 bytes at once. Not always it does mean that it's gonna be faster than using 2 instructions, to be honest, and that's the case here. So that's one pushing is just 1 cycle and push W is 2 cycles. It's like using 2 pushes of 1 byte. It's actually 2 seconds. Sometimes it gives you again to use the instruction which is wider. Sometimes, like in this microprocessor, it's just that we have 1 instruction instead of 2. The execution time is the same. And then very often we've got the instructions which are not really necessary, basic arithmetic, incrementing and decrementing. Why they are quite often available? Although not necessary, because increment is what? Adding 1. Decrementing is what? Subtracting 1. So what's the sense of it? It's for shortening the notation, so for simplifying the code itself. You can, instead of incrementing and decrementing, usually you can just make add 1 or subtract 1. It has usually the same completely meaning. It usually gives you no gain in speed, but it's very often the incrementing and decrementing for the simplicity of the code, so that the code is simpler. Because this instruction usually requires just 1 argument, what is to be decremented, while adding, subtracting means by how much we are decrementing or incrementing. Sometimes in some microcontrollers, incrementing is shorter, sometimes. Because adding and subtracting, there must be a place what needs to be added, to what register we want to add, and what value we want to add. So we have 2 arguments. In case of incrementing, we have just opcode and what register we are incrementing, because it's always by 1 or by 2, or decrementing by 1. So sometimes the decrementing is a bit faster than adding and subtracting, not in this microprocessor, but usually incrementing and decrementing is there. Also we have a version for word. Then we have got also very important arithmetic instructions of testing, various kinds of testing and comparing. Usually we have just compare, so CP, CMP, this kind of. Comparing is actually subtracting. Subtracting with neglected result. Because what compare does is take register 1, take register 2, subtract them from each other. And do nothing with the result, because result is not important. What is important is the result. So if the result was negative, positive, or 0, 3 things we are testing. That's how it is done formally. So it's basically subtracting with not important result. Also, we have some testing non-zero, if not 0, and that's a bit testing, bit comparing. I think it is, but to be honest, I'm not really sure. We'll check it out a bit later. Then we've got various logic operations as well, something always present in every microprocessor on the market, and in every microcontroller that you can think of. Very basic operations: AND, OR, XORing, and complement. CPL is complement. Standard operations. You could think about NOR, about NAND, about XNOR. Usually not present, but they are usually not important. So AND, OR, NOR, not. Still XOR is extensive, because theoretically having AND, OR, and complement, we don't need XORing, but here we have also XOR, because XOR is used for negating bits. XOR negates bits, because if you XOR a register with some mask, of course you negate whatever you want to. So if you have, in case of XORing, you should remember the kind of operation. So then if we have the register 110011 and we XOR by, if we XOR by it, then we negate those positions. So this is 0, this is still 1, this is still 1, this is 0, this is 0, this is still 1, this is still 1, this is 0. So we XOR wherever there is 1. We negate this position. So it's useful. It's useful to XOR. That's why it's here. Although again, we could have just AND, OR, and NOT. That would be enough. Then we've got bit testing, bit operations, and bit testing and jumps and various tests and branches. This is a bit unique in case of microprocessor. Not all microprocessors honestly do have this kind of operations, because not all of them support direct bit operations. This is the microprocessor that does it, but not all families support it. So we have bit setting, resetting, complementing, bit test and jump if true, bit test and jump if false. This kind of operation. Not all microprocessors have them. 8 bits very often, the larger ones not usually. Then arithmetic operations. The basic set of arithmetic operations is just about negation, adding with carry, adding, subtracting, subtracting with carry, period. This microprocessor has additionally multiply, divide. Multiply and divide. I don't know if I've told you, but in case of 68 family of Motorola, adding and subtracting 2 cycles, multiplying 10, dividing 40 cycles. So that's how complex division is. And here in this microprocessor, it's there. It's not single cycle, to be honest. It's also quite long. It takes 10 cycles or something like this, but it's there. So you can use division. You can divide 2 numbers.
And there is a special block to do multiple.
Yes, there is a special block internally, of course, to do multiplication and to do division. That's why it's there, because normally, sequentially, multiplication would be very, very long, because instruction decoder theoretically could make a loop and then do it in loop version, because that's the simplest way, the most resource efficient way, but the longest execution time. Same is with division, because division is subtracting. Yeah.
Do you know maybe if C compiler can use can make use of bit operation?
It does use. It does use bit operation. It does use bit operations if possible, of course, because we've got the compilers for particular machine. So there are no universal compilers. So there is a dedicated compiler for this family, for this family, for this family. So of course, for this kind of family, for STM8, of course, they are using bit operations because they are efficient. They are very efficient in bit operations. Shifting and rotating. Shifting, rotating, swapping. Because we have swap, we have various shift, left, right, arithmetic, non-arithmetic, over carry, with carry, without carry, depending what you need. Because we discussed about it, I think, last semester. Discussed about it. I try to show you the difference between arithmetic shifting and logic shifting, because with arithmetic actually we take care about the sideness, because you know we have U2 notation, so we take care about sideness. About the arithmetic, for the arithmetic, all the shifts and rotates. For the logic ones, we don't care. It's just plain stream of zeros and ones that we are moving left and right. Here in this microprocessor, although there are so many shifts and rotates, they are always by 1. So if you want to shift or rotate by more bits than 1, you have to repeat this instruction a couple of times. It takes time. In better, faster microprocessors, we've got the versions of shifting and rotating by a few bits at once. It's especially useful in 32-bit microprocessors where we want to shift by, let's say, 17 bits. So instead of doing shift by 17 times, repeating it 17 times, we are doing just with one instruction of shift by 17 bits. But this requires a complex barrel shifter. It's a complex logical structure inside this barrel shifter itself. Yet, why do we need shifting and rotating? Because it's not only about the logic operations, but the shifting and rotating, especially the arithmetic versions, shifting. Rotating is not here, but shifting can be used to supersede multiplication and division. Because you know 2 to the power of n, where n is negative, is a division, and 2 to the power of n it's a shifting. So when we shift by n bit left, then it's like we do 2 to the power of n. If we shift n bit right, then it's as if we made a division by 2 to the power of n. So for microprocessors, we found division, or if we want to just divide by 2, you know, this division will take you 10 clock cycles, something like, if I'm not mistaken, it's about 10 clock cycles, and shifting is 1 clock cycle. So if you want to divide by 2 or 4, it's faster to do it with shifting than to do it with division. various calls and jumps. So various versions are absolute, extended, with some conditions. All this is here, call it as well. Then we have returns. So returns from functions. Returns from functions. So return means that the actual value on stack pointer is loaded to program counter. That's how the return function works. Instruction. So it's taking whatever is on the stack pointer and placing it in the program counter as the next instruction pointer. Nope. What do we need? Nope. Naturally, the nope we need for doing nothing. No operation. Sorry, one mistake. We are doing nothing with nope, but nope is for precise timing. Nope is used always for precise timing because nope is almost always single clock cycle. So then we know that the nope is always 5 nanoseconds or 50 nanoseconds or 15 nanoseconds, whatever our clock cycle is, clock period is. And then if we use 20 nopes, we know that the delay will be exactly the value, the 100 times the period of the clocking. Then we've got jump relatives, so those closer jumps. Then we have interrupts. The next group, the management of interrupts, so mainly the software interrupt trap, and putting everything to sleep, that is halting the microprocessor, very common today, so that we stop the microprocessor itself, the CPU, so that it goes to sleep, then it has to be woken again by some peripheral, and the IRET, so return from interrupt. So also the instructions which are always present today in microprocessors, and then condition flag modification. Here we have two instructions for enabling and disabling interrupts, but this is also for setting, for artificial setting of the flags, because the flags are set normally by arithmetic logic unit. Because when we have the AND operation and we have a carry, then the carry flag is set. But we can usually, there is always a chance, for some reason, although that's not very important in practical usage, but there are always some instructions for modification of the particular flags. Or we can change the whole, in some microcontrollers, this is also the case, because we have access to the conditional register, condition code flag register. So we can modify the whole condition flag register if we need it, although normally we just need these instructions, to be honest. And break for break as a breakpoint may be less important at this moment. So this is the summary of the instructions, and all microprocessors on the market have a subset of these instructions, or maybe some categories are extended. But this is really a good view of what we can have. In case of these categories, that's all we can expect from assembly language, from assembly instructions. And then whatever we write in assembly, we have to use the instructions from this list. If we write in C compiler will compile our code to these instructions. Yet you can see already the difficulties we get with assembly in the language, because comparing, especially if you're accustomed to C or Python or whatever language you're using, those instructions are completely different from the instructions we have in higher level languages, completely different. The reason for this is that these instructions come directly from this state machine, because when we have the finished state machine with data path, because that's the structure of the CPU, and quite natural are these kind of instructions: loading, transferring, bit operations, logic operations, various jumps and calls. So these are natural instructions from machine point of view, while C language, Python, Pascal, Java, whatever, these are the languages closer to our thinking as a human being. So that's why programming in C is completely different than programming in assembly. This is far closer to the hardware than, of course, than the higher level languages. Okay, and then how to read the table, because we will not, I have some slides with the instructions taken from the documentation from the manual of STM8. Of course, we will not analyze them because there is no sense. So if you need some details about the instructions, just open the manual and you will see. Just how to read this table. How to read this table. So we have a table describing some instruction and how to read the table for this particular instruction. So what is happening? So for example, let's take the last one. So the and. Let's say what is here. So we have in the table the mnemonic. So this is and how we use it in assembly. Then we've got very short but very brief but description. So what is this? So it's a logical and, for example, or adding add word with carry without carry. This is add with carry, for example. And then we have what kind of bits are modified, are affected in CC register. It's very important information. What bits are affected, and for example, this adding is affecting just bits negative and zero. So bit N and bit Z. So if the register is 0, then Z is cleared. If this is not 0, then it is set. If it is 0, it is set. If it is not 0, it is cleared, because this is showing us if this is 0. This is just for bit 7, for R7, so for the 7th bit, for the most significant bit of the register. So in case of using it for accumulator, this is of course the most significant bit of the accumulator. So if the final result in the accumulator, the 7th bit is set, then it means that you have negative value, so the bit N is set. If bit 7 is 0, then this bit is 0. It's so simple as this one. But here, for all the instructions, naturally we have just a bit different behavior. Then we've got an example of the syntax in some chosen addressing modes. Because in this table, this microprocessor is having multiple combinations, really a lot of combinations, so we can have, of course, not every mode fits to every instruction, but some instructions like this one you can see here, they accept most of the addressing modes that I showed you in the beginning of today's class. So here is just an example of the addressing mode. Some microcontrollers, especially the RISC ones, they have fixed addressing modes. We can say almost inherent addressing modes, because in CISC mode, in very pure RISC microprocessors, the one instruction is usually one addressing possibilities. Here in this microcontroller, we've got various addressing capabilities. That's why here just an example with against the stack pointer. And then we have what the instruction is doing, so the operation that is being conducted during this instruction. So for example, here we have the to accumulator, there is assigned the accumulator and whatever is in the memory under the stack pointer plus the short offset. So this is 12 hexadecimal, so this is 18. Stack pointer plus 18. So this is the address in the memory. And here we have the mnemonic. The mnemonic is of course here. Here I have the machine code. This is the mnemonic. This is the machine code. 2 bytes. 14 BB. 14 BB. Where BB is this. Actually in this instruction. So this is BB. 14 means that this is AND A and stack pointer against stack pointer, and the BB is this offset. 2 bytes. That's how it is. So that's how it works. And it takes 1 clock cycle. If there is no pipeline stall or problems with pipeline or sequence of comments, it's just one instruction. Once the clock cycle is the execution time. For words, take a look, 2 clock cycles. Ending, depending on the addressing modes, 1 clock cycle, 2 clock cycle. As well, also interesting to see, take a look. We've got the ending with this complex theoretically addressing modes, so there is an offset against stack pointer. This instruction takes 1 clock cycle. But this instruction, when we add to stack pointer, want to add to stack pointer a value, this instruction takes 2 clock cycles. That's how it is. Sometimes it's more difficult. Why is that so? Actually, the reason that is that here we've got the accumulator, which is 1 byte, which is 8 bit long. And stack pointer is 16 bit long. It's a longer register. That's why the operation takes longer. It takes 2 clock cycles and not one. That's how we read this table. That's how we read this table. We've got, of course, much more in this table showing us the complexity of this microprocessor. Yeah, take a look how long, for example, this absolute call takes. 6 clock cycles. That's absolute call, because this is call with absolute value. 6 clock cycles it takes. A lot of things is happening. That's why it takes so long, because we have to push everything on. We have to increase the program counter, but then we have to push on stack the low and high value of the program counter and put the value, this WW and BB, we have to put them into the PCH and PCL, so the higher and lower bytes of the program counter. Actually, a bit interesting is that with the call F is shorter. I don't know why, but it takes 5 clock cycles instead of 6. Although here we have a longer. It's actually the call F here. It's a jump because it's not none. Ah no, okay. It takes shorter time because it's taking the data from external memory to program counter. So we don't push this value to the program counter, but it takes from external memory. So it takes shorter time for this core to take the data from external memory and put them in program counter than to take them from the instruction and put them into program counter. Anyway, various times, 5, 4, but here we have instruction shorter, longer, all these instructions. Many capabilities we have here. Yeah.
Why it's incrementing program content by 4 bytes?
Which one?
Let's say call.
Yeah.
And first thing it does, it's incrementing quantity.
By 4 because this instruction takes 4 bytes.
Oh.
That's why it's incrementing by 4. Pointing to the next instruction. It's already a break, but one last remark. The idea about RISC's microcontroller, microcontrollers and the use of RISC's microcontroller and the simplification of RISC microcontrollers also lies in this area to unify this very nasty feature that we have here, that this instruction is just 1 byte and this instruction is 4 bytes. Because in here, instruction decoder has to be very clever because it reads the first byte and then sees, okay, I expect 3 more. Or it reads 8B and say, okay, this is just 1 instruction. So the program counter, the incrementing of the program counter is variable in case of CISC, which is here in this microprocessor, which means that there has to be a lot of logic included in the structure internal so that everything works. In case of RISCs, we will talk about, for example, PIC micro in a few weeks. You will see how simple it is there inside, because the instruction is always incrementing program counter by 1, because 1 memory cell, 1 instruction. Memory cell in case of RISCs is usually dedicated, like 17-bit, 14-bit. Same is in our microcontrollers. In our microcontrollers, we've got 32-bit, let's say, because there is 16-bit instructions for TAM2, but in the beginning, original ARM is 32-bit, 1 instruction, 32 bits all the time, always. So then PC needs to be incremented by 1 only. Here, as you can see in CISCs, this is a problem. This is a discerning feature between CISCs and RISCs, and it's about guessing. So first of all, this is variable, because we have 1, but we have 6. When we have a division, there should be, where is the division? Oh, 16, not even 10.
Those instructions add to the PC the number of cycles times?
Number of bytes, yeah. No, because number of cycles, it means how long the instruction will be processed. And to the program counter, how much space does it take how many bytes are there? Maybe
so
this one.
The instruction has 2 bytes, the PC will be added 2?
Yes.
Okay.
So for example, this instruction, this division, div W, program counter will be increased by 1. because we have just 65 and that's the instruction. Take a look how short the instruction is.
But isn't that 2 bytes?
No, it's 1 byte. This
Okay.
is just 65 because this instruction
So
to
this is-
inherent addressing mode, because this instruction is dividing x by y. So take a look. It's x. The result is x by y, the integer value, so the quotient in x, and the remainder is placed in y after this instruction. But this is the instruction with inherent, so-called inherent addressing mode, because we have no option here. We are just writing div w x/y, but there is no option, no addressing, no options we have here. That's why just 1 byte, which is good because it takes only 1 byte in the memory. Program count is increased just by 1, but it takes 16 clock cycles. So the next instructions will be fetched from PC plus 1, but it will be fetched after 16 clock cycles when this instruction is finished. So the length here and the number of cycles, these are completely different things. Here we have 4 and 4, for example. Here is 1 and 1, 1 and 2, 4 and 4, 2 and 2. But here is the extreme case, 1 and 16. So short instruction, very short, but very long time it takes for it to execute it. That's how it is. Okay, already on the break, so let's make 15 minutes break and we'll get back after this 15 minutes. You know, memorizing instructions, I don't like to memorize from practical point of view. I don't think it's a good practice to memorize the instructions theoretically. So if it's the best to memorize the instructions automatically if you start using them. So of course you must know the categories, you must know what you can do. So basics about your addressing modes and basics about that there are logic instructions, there are arithmetic instructions, there are program control instructions. But more details will follow for if you need the instructions in greater detail. Of course, there is a manual for it, and in the manual you just search the manual, and you just must be able to read this manual. So you must be able to, don't freak out when you see this kind of table. Just read it, read the information you need from particular columns and rows in the table. And that's my advice. So don't, yeah?
I have a question. So basically, that's all the instructions that are in assembly language, right? And using this instruction, we can somehow program any controller or only
this particular controller.
STM8.
STM8. Although the instructions are very common between different platforms. They are very common between different platforms, and if you are able to program in with this set of instructions, the STM8, it will be very easy to jump between different CPUs. Although they are CPUs with simpler instruction lists and CPUs with more complex instruction lists, because I know different kinds of CPUs, and really this is somewhere in the middle. It's neither most complex nor the simplest. Yet this is on the assembly level.
So, like any compiler of C or C++ language contains like different list of instructions for different
Of course.
controllers.
Of course, different lists of instructions, different lists of registers, and different capabilities in case of addressing modes. Because then here addressing modes are not shown, but as proven earlier, there are a couple of addressing modes here, and many of those instructions exist in various addressing modes. In various addressing modes, and compiler knows C or higher level language in general compilers. It knows what it can use for efficient application. If you are doing assembly language programming alone, which is the idea this semester, at least for part of the semester, then I want you to use this instruction. So you have to try to use this instruction. It's different, you know, it's different. Sometimes it's still useful. So of course it looks completely weird in the beginning and a bit crazy because it's completely different from human language and from the programming languages that you already know. But that's the way it is. it's closer to hardware, so in some situations we are still using it in practical applications, the assembly language. We are still using it for getting the most out of the CPU that we have. Nowadays nobody writes the complete code in assembly language because it's too difficult to understand this code. So the problem is with debugging this kind of code, this kind of because the machine language is not very human friendly, so it's very difficult to debug this kind of language, and the code is not very readable. That's why the complete structure, nobody does it this way. Although I remember times I did 40, 50 kilobytes code just with assembly language once for some microcontrollers, so yeah, it took me a couple of months to be honest, but it was possible. Nowadays I wouldn't do this, and nobody does it this way. There is no sense in it because the structure is much simpler and much more human readable, friendly to do the structure in the high level language. But still, to control what is happening, still to keep the real-time operation and to get the most out of our CPU unit, yes, quite often, or sometimes, not quite often, but sometimes we need to get down to the assembly language. So remember, you are in the studies, so it's time for you to learn sometimes clear things. Not very simple one maybe, but the things that will extend your capabilities a bit, so that you are not, because we are here to give you tools and to give you knowledge that there is a chance to do this way, this way, this that way, so that you can choose in your professional life which is the best way and the most efficient way of doing things. I don't say that you will be for sure using assembly language in your future life, but if you don't learn it now, today everybody wants to go simple. So everybody wants, okay, so if we are not able to do it with 8-bit, let's take 32 bits, and if we're not able to do it with 20 megahertz, then let's take the 200 megahertz unit. Okay, that's also the way today, we are doing it today. But sometimes we really get to the edges of the capabilities. We have a hardware and it's too expensive to exchange the hardware, and we have to fit our application into this very small tiny hardware that we have, or into the hardware that we have, because in case of assembly it's not only about 8-bit microcontrollers programming, sometimes we need to program the 32 bits as well, and then we have to turn to assembly. Another language, another example why the assembly language has a sense really still today in applications. There is a very nice microcontroller, digital signal controller it is called, with 2 or quad cores from Texas Instruments. It has 2 cores which are programmable with C. One, if in dual core mode, it's 1 core programmable in C. In quad core mode, it has 2 cores which are C programmable. But the other two cores are working in coprocessor mode. And for some reason, Texas Instruments is not supporting C programming. There you have to write an assembly language. Those 2 additional cores. They have limited functionality because they are called control law accelerators. So they are just for very particular calculation examples, calculation applications or arithmetic applications, but still only the assembly language. Yeah, so just treat the assembly not as your ultimate way of writing a code, but the assembly is just to learn the essence of microcontrollers and microprocessors, and treat it this way as something extra that you become an expert in this. So you don't have to be an expert, but that you will know this. You will know that something like this exists. Sometimes it may be of use to you. That's how I want you to treat the assembly. Of course, the C is dominating today in microcontrollers, and it will not change. It will change towards Python. That's the future, I think, the nearest one, but not in case of assembly. But the assembly is still sometimes in need. That's how it is. Like the logic. Not always we can use microcontrollers. Sometimes we have to use FPGA, CPLD, AC. So sometimes we need to use even harder description languages, but that's another story. Okay, let's go further. Again, assembler and linker, because even if we don't use the assembler instructions, still compiler automatically transfers our code into assembler automatically, and then from assembler to object language. and universal one, and then links everything together, the various objects together with libraries to form final hex file. So, what's happening under the hood? So what's happening when you press compile or build solution? Couple of things are happening. So many things are happening, in fact. Because when we are writing our project, when we are preparing C files, CPP files, or S files. S for assembly, C for C file, CPP for C++ files, because every compiler today is supporting C++. In case of Python or Java or whatever C#, that's for microcontrollers not so obvious, but every microcontroller compiler supports those three source files. And then those source files first are converted into assembly files, assembler files. If we have the S file, so if this file is already in assembler, then this step is of course omitted because the file is already in assembly language. But if we have a C file or C++, then the first thing that is done is that every line is translated into a sequence of instructions, these assembler instructions. Then if we choose optimization level, then the file is parsed again and it's optimized. But still it's optimized on the level of assembly language. That's something you can easily see because there is always, when you have a C compiler for any microcontroller, there is always a file, a listing file, map file, so there are different files here as a transition, as a report files for reporting the progress of compiler that will show you how the C is translated into assembly and how optimized it is, how it looks the code in assembly language after optimization. Various level of optimization, but we don't have time here to talk about it. Then from those source files, so assembler optimized or native or written by a developer source files, assembly files, there is a compilation going on. So assembly there is going on, and from the assembly we get object files. Object files which are not text files anymore, because the assembly files are text files. Even if they are after optimization, they are still text files. And then we get object files with the internal structure depending on the compiler. Compiles to some, let's say, internal pseudocode, relocatable pseudocode, because then there are no direct addressing, so every procedure is relative in case of addressing, so that they can be. When we have this object files, then additionally we've got the libraries. Libraries, as these are procedures which are already delivered to us written by somebody else, with some procedures that are already prepared. Many such procedures can be, many libraries we can have on the market. Simple things can be, so for example, we can prepare our code from earlier projects, and we can store the code into already precompiled library files, or we can take the library files from GitHub or from internet or from whatever we want. There can be very interesting things in the libraries, like for example FFT analysis or neural network supporting procedures, I don't know, matrices, complex numbers, various things we can have. So even if we are writing in assembly code, mind that, it doesn't mean that we can't use this library file in our project. Of course, it's completely reversed. In assembly language, it's even better to use the predefined structures and functions, because then it's simpler. We don't need to write it down in assembly, which is sometimes difficult. We just take something that somebody has already done for us for free or not.
Are they libraries like universal or specific for one type?
Specific. The libraries, because take a look, they are here. They are the libraries, because we can have also the libraries here at this level.
Mm-hmm.
So we can have the libraries which are written in C code. For example, you can take a MATLAB, you can write in MATLAB some algorithm, and then you can convert this algorithm to C. And then this is universal. So then these are the libraries that you add as a source files, which is not very efficient. So what MATLAB generates is horrible. It's really a disaster what MATLAB generates. It's so unoptimal, you wouldn't believe, and it's so difficult, because MATLAB itself, when you run MATLAB procedures in MATLAB themselves. They are written in assembly. They are heavily optimized. And really the most time-critical elements, the most time-critical parts are written in assembly language for PC by experts, you know, because if somebody knows the assembler, he's an expert. C is not an expert, but assembly is. Somebody did it in MATLAB, and it's in assembly, but the procedures that are taken from MATLAB, you can write in MATLAB 2 lines of code, they will be efficiently executed in MATLAB, but you convert them to C and then you compile them and run them on a PC. After compilation, they are a few times slower, usually a few times slower. And of course it is possible to take the procedures in C written and put in assembly, right? So you can take the MATLAB and, for example, try to use them on STM8. Why not? So of course, simpler procedures STM8 can handle as well. So maybe not some complex matrices and complex transformations, but simpler procedures, why not? But still, they are very inefficient.
So this transformation from MATLAB source file to C source file is going like MATLAB is compiled to assembly language and then from
No. Unfortunately, no. Because in MATLAB it is universal, so you can take the C files, so they are not platform dependent. Which means they are universal, so it means that you can compile and use them on any platform. That's actually good. But this means that the files have to be universal, but they are, because of the universals, they are very inefficient. They are very inefficient.
So I think that there is a paid option to like make code specifically for like Cortex, ARM Cortex. So it can have some assembly.
Yeah, maybe. Yeah, there is a chance. I haven't had any experience with this function. Still, I don't believe that the universal code generation will be as efficient as rewriting code. Still, I don't believe it. Of course, it can use special features for the particular platform, because it's important. The use of special features is important because, for example, in case of microcontrollers, we've got the pipelining, and sequence of instructions is extremely critical in case of pipelining. Even for STM8, which the pipeline is of only 3 units, there are 3 units fetching, decoding, and executing. But in Cortex's M, and especially Cortex's A, we talk about superscalar, multiple pipelines, so 20 stages, for example. So here, feeding the stage with data is extremely critical. So for this reason, special generators, okay, of course, will be better, but still, I don't believe they are going to be as efficient as writing everything. Maybe not even in an assembly code, but writing in a dedicated compiler for dedicated platform. That's still, from my experience, years experience, it's always more efficient. Even if you don't write in assembly. Assembly is extreme place, but even if you write in C, but write dedicated platform, dedicated compiler. That's how it is. So we can have libraries here. Of course, more efficient are libraries here. And if you notice about the STM microcontrollers, they have fantastic. We'll talk about it by the end of the semester, maybe beginning of next semester, about the CMCs. So it's a fantastic, fabulous set of libraries which are actually included here with dedicated functionality, aforementioned FFT. So, but of course, there are libraries for Cortex M0s, for Cortex M3s, for Cortex M4s, for Cortex M7s, of course written in assembly language and with dedicated instructions for M7, because there is difference between M7 and M0. More details, of course, will follow. But those libraries here used to be very optimal. So if you have a chance, if you have a choice libraries at this stage or at this stage, of course, this is better. This is better and more optimal. Then we have a linker. So it is written because these are the tools from STM8. So link, assembly, ops, and upslist. The names are a bit different between platforms, but the functionality is the same. There is always some assembler. So there is a compiler here that makes the assembler a file. From the assembler, we always have a linker that makes the final file, because the linker actually makes the final file. Here this is COD, but there are different extensions. Actually, there may be bin file or whatever the platform has, but this is the final file where all the functions are linked together to form one final file, one binary file. It's of course not executable file, because there is no operating system to execute the file. There is a file that we that we just upload to memory, because that's how the execution goes. So we have to upload it to the memory where the execution is performed, the program memory. So of course the very important in case of linker is the addressing. So here the linker itself linking all the objects plus the make file, because usually there is a sort of make file that sometimes we have to edit it by ourselves, sometimes it's under the hood automatically managed by the development environment. And this make file, actually the most important in this make file is to put everything into the space that is for the particular processor proper. So because some processors have to have the code in this addressing space, another here, so it really depends on the particular platform what is the addressing. But actually this code is simply speaking, just the address value of the memory cell, address value of the memory cell, address value of the memory cell, and that's what this opsend is doing. Here it is opsend, but again there are different applications for doing this. This is translating the binary file, this is the output binary file, into a programmable file. It is written binary, but it's not true, it's a text file. It's a text file, so S19 and hex or hex file, because they are two standards today on the market, Intel hex and Motorola hex records, with dedicated, okay, I have it somewhere, let me do it this way, just skip a bit, output file generation, we can speed up the things. Yes, we have, each line of the files have a certain format, but they are again a text file. So this hex file or S19. So these are the output files, which are for us the most interesting from if we want to program. These files actually consist something like this: that we have the address and we have the data. So at what address, what data are to be placed? It's a text file, so it's, I don't think I have some example. For example, srec file, because I don't know if we have enough time to analyze everything. Oh, I will show you the file, maybe this way. So here are the options that we have in Motorola S file, because there is Intel hex and Motorola hex. Actually, it's a text file where there is a simple character, a simple line of string. And the strings are consisting of some header, the address, and the data plus the checksum. Everything is in the text format. Yeah, to show you how does it look like. Let me open something. Here it is. That's how the output file looks like. That's how the output. It's a text file. It's a pure text file. This, of course, this is to be decoded because this is the. This is not the Motorola S file, but this is Intel hex. Although here is the difference is that there is a percent mark, there is a colon, but the idea it's almost the same. So we have the number of data, the address, type of record. So these are the particular bytes, and then the data itself and the checksum. So the checksum is 2 byte, 1 byte, 2 byte. So there are slight modifications, but the general rule is, as you can see, the same. So address, and at what address, what data are there to be written. That's the output of our linker. That's the output of our linker. Additionally, Additionally, so let's close it for a moment. Or minimize it. Additionally to this, yeah, let's go back to this chart. So this is here. So this is here. But additionally to this, we've got listings or map files, because again, it's a bit different between the platforms. We've got always a listing, text listing, showing us or telling us what was happening and what every symbol, every procedure, every function, where is it in memory, where to expect it, how large it is, how much space is occupied by variables, by procedures, by constants, for example. All this is always present, always available in every compiler. There is always some sort of map file. So again, to give you some idea how does it look like, to give you the, here is, for example, the binary file. How the binary file is looking. Yeah, this is the binary file. So this is the input. So of course these are just numbers, but we can read nothing out of it. So this is the binary file. So this is this here. So this is this kind of file. So in this actually this environment, it's out, not code, but out. But believe me, that's nothing. It's just different extension, but the idea is the same. Yes, but here you have the map file. So the map file is really useful file if you want to get some ideas what is in the file itself. And so we have, for example, memory configuration. So in this processor is a bit more complicated than the STM8. But here is for example, the origins of the various areas in memory with various names. It's configured in the map file. But there is the origin, the length, how much of this area is used, because it's this the predefined length of each sector, for example, how much of the sector is in fact used in the current project. So it's more or less. So of course it means how much we still have. For example, we still have left. But not only this can be read from the map file. So as you can see, peripherals, for example, are even here placed. There are particular peripherals in this microcontroller. The address, the offset of the peripherals, how much the peripheral gets, that's maybe not that important, but the important thing starts here. So we have the information about various objects, where they are in physical memory, at what address, and what's the length. For example, this kind of object is here, and it takes this much of everything in hexadecimal value. Yeah, certain variables there is, because they are functions. So all this you can read. So if you need something, take a look how long this is. So everything is here with how much of each section does it take. But that's also not all the information, because with this listing, this is the map. But there is also another thing I wanted to show you. Let me find it. A lot of information is under the hood. That's what I want to prove. A lot of information, not always very useful, at least not at first sight, but sometimes very interesting. Maybe not for you at this moment, but you will find them interesting if you start doing something. Where is it? Okay, so I have too many files. Anyway, maybe let's go back. We don't have time, we have 5 minutes. So maybe let's go back. I will show you next week when I find it. So this is the process. Actually, this is the process of assembler and link of making a code. This is the process of making a code with the stages. Now, in case of assembler, now let's go back to the assembler. So because that's the last thing I wanted to touch, but unfortunately we have to transfer part of it for the next week. In case of assembler, the syntax of the assembler, because that's something that I want you to play with this semester. That's why a few remarks about the syntax, because the syntax of assembler is naturally different from the syntax of the C code that you are accustomed to. So first of all, in case of assembler, it's important if the code, if the opcode or mnemonic is where is it placed. That's one different thing. In case of C, we can put everything in line 0. In case of assembler, in line 0, we are allowed to put labels, while the opcodes must be a tab or at least one space from the left side, from the left corner. Then we have from the left side of the screen. Then we have the operand, if they are operand or operands. In case of this assembler language in STM8, there is if we have 0, 1, or 2 operands. So we have 3 options: 0, 1, or 2 operands. 0 operand is an inherent mode, so from the description we know what it does, like an op operation. In case of 1 operand, then it's also very simple to understand what this operand means. But then we have the 2 operands. In 2 operands we have destination and this is a source. So from this address we put something to accumulator, for example. In more complex microcontrollers, we've got 3 operands. We've got 3 operands, and for example, we've got LD, A, B, C, not LD, but LD of course it has no sense, but let's say add. And in this case, we don't override the source. It's the advantage, 3 operands. It's the advantage because we've got the situation that A is assigned B plus C. Because here, we always override one of the sources, because this is source 1, this is loading actually, but if we choose put add, this is the source 1, this is source 2 of argument 1, argument 2, and we override the argument 1. In case of the 3 operands assembly language, we don't override the source. That's the advantage. But 8-bit microcontrollers, they never have. I have never seen an 8-bit microcontroller with this method, with the 3 operands. Just 2 operands, 0, 1, or 2. And then we've got the separator. That doesn't have to be, but this is the comment. Each programming language, for some reason, has different signs for comment. I don't know why, but that it is so. And it's as well in assembly. So it's semicolon is the comment. And from the semicolon under the end of the line, we can write anything because it's treated as a comment. And we have 1 line, 1 instruction. That's also a difference. We can't make the instructions because it's white space sensitive, we call it, the assembly language. C language is white space insensitive, so we can have 1 long instruction split it in a few lines, or we can have in 1 line many instructions. Here we can have 1 line, 1 instruction. 1 man, 1 vote. 1 line, 1 instruction. Same. In case of operands, we can work on accumulator, we can work on index registers. Again, depending on the addressing modes, depending on the particular instructions, we can work on the XA, on the high and low bytes of X or Y. We can work on stack pointer or on conditional code register. So these are the operands that we can use, usually as a destination, but sometimes as a source. So some examples you have already seen. Naturally, the addressing modes for the short, long, and extended addressing. So again, this has already been. Then the last thing to finish, the last slide, the labels. So the syntax of labels. The labels are, in case of assembly, again, it's a different method of writing a code. You know, in C, if I can see students using a goat in C, then I tend to take my axe and cut and chop the hands off. Generally, GoTo should never be used in C. Code written in C or C++ or even high-level languages with GoTo is faulty, I would say this way. But in assembly, it's completely otherwise. It's completely different. Here, we mainly use, we don't have GoTo, but jump is something like GoTo. Branches will GoTo, actually. Of course, it's a different way of GoTo. So we are basically, in case of assembly language, we are mainly playing with jumps and branches and calls. And to use jump, branch, or call in case of assembler, we have to use kind of labels, because we go to some label. Of course, we will not count the addresses by manually, because it has no sense. Why we can't have them manually? Because usually the code, the absolute addresses we get only after the linking. When we write the assembly, when we write the code, we don't know the addresses, the exact addresses of a particular procedure. Only during linking, the procedure is assigned the physical address. So it means that during the writing, we have to have some abstract idea of the addresses, of the placement of variables, of placement or of code, and we do it with labels. So labels are extensively used. In C, we can also use labels, you know, but the labels are only for description or for GoTo, but again, chopping the hands off. So no GoTos, here no labels, here labels, yes. And the labels, take a look, must start in column 1, are case sensitive, so like in C, up to 30 of the following characters. So we can't use any character here. We can use just letters, digits, and underscore, not much choice. So no pound signs or dollar signs or whatever you want, or asterisks, nothing like this. So it's a simple thing. The label, but the labels are very, very commonly used in assembly language. We are off time, unfortunately. Again, I failed to deliver the whole content I planned. We have to live with it. See you next time. Thank you for your attention.